and they need to cool themselves some days, right? So maybe some days if they're hot, they stick their ears out like that, but most of the time you probably don't see them sticking their ears out because they probably don't need to lose all that much energy each day. Right, so that's my introduction to the next chunk of climate physics that we're talking about, which is how much and what kind of radiation things emit. But there's really only like one main kind of thing that we care about, and that's called a black body emitter, or a black body object. So a black body is kind of physics lingo for a perfect emitter, a perfect object. Right? And if we have something that acts as a physics black body, it's going to absorb all of the radiation that hits it. That's why we call it black, because it doesn't reflect anything. So something that doesn't reflect any visible light, like my stapler, looks black. Right? So a black body would not only absorb all the visible light that hits it, but absorb all of the everything light that hits it. Color of an object, though, and this is not, actually it's a terrible example. Color of some objects is a terrible indicator of if it's a black body or not. So I'm not going to get this. The sun, what do you think? Black body or not? Doesn't look very black. But it actually, the sun is nearly a perfect black body. It's just that it's so hot that it actually is colored. But no, the sun is actually a near perfect black body. We are pretty darn good. No, we're not pretty good. The sun actually is. So anyway, that was confusing. I should have saved that for the end of class. Yes, Brian.
Is a black hole a perfect black body?
No, because it doesn't emit anything.
It's close.
It doesn't emit anything. So black. So a yellow star is actually a near perfect black body, but a black hole is an extremely imperfect black body. Yeah.
You can explain it.
It doesn't.
It means anything. You can say anything about it.
Yeah, black body isn't a black hole doesn't emit a darn thing.
No, but why does that matter?
It's on the board.
Yeah. So I opened this can of worms by asking about something we weren't ready for. So yeah, let's rewind, catch up a little bit, and then come back to sun versus black hole. All right. A black body is something that does absorb all the radiation that hits it, but more importantly, it emits perfectly. Right? So it emits radiation like a perfect absorber would. Right? So really a black body isn't so much a perfect absorber, it's a perfect emitter. Right? And so yes, a black body does absorb everything that hits it, but more importantly, it re-emits like appropriately. Now, this is the graph that our objective referred to, which is a graph of radiative power on the y-axis as a function of wavelength on the x-axis. I'm slightly lying. This particular graph doesn't actually have power on the y-axis, but it has like energy. I can't even read the axis, but it's something very related to power. So when we say radiative power, that's like the sun. The sun emitted how many? 10 to the 26 watts of electromagnetic radiation, right? So this is kind of measuring that. How much electromagnetic radiation are we emitting? And then the x-axis is, what is our wavelength? So there certainly is a peak wavelength. There is a wavelength of electromagnetic radiation that is more than all the other wavelengths. And then we reach that peak pretty steeply, but then we leave that peak wavelength a little more shallowly. So this black body, right, doesn't just emit one wavelength, it emits a range of wavelengths. And really, truly, it does emit some power at every wavelength. So this would kind of asymptotically reach a power of 0. This actually does also. Right? So there actually is a small amount of power even at these radio wavelengths and even at these gamma wavelengths. But for this particular body, I think this is probably for the sun. So most of the, in fact, now that I stand even closer, I can see the demarcation line between visible and infrared, and then visible and ultraviolet. So the peak wavelength that this thing emits would be visible. There's lots of ultraviolet, there's a fair amount of infrared, very little other stuff. So let's talk about this just a little bit more. Where's the sun? What can I use to be the sun? Yeah, I'll use the earth as the sun. That's too confusing.
Kevin.
Kevin?
I mean, I agree with that.
I don't have anything great, but this, no, here, this is the sun. Alright, this is the sun. It's yellow, orange, it's kind of like the sun. What's the temperature of the sun? Anybody know? It's a little less than 6,000 Kelvin. I think it's like 5,800 Kelvin, right? Yeah, so let's write, and you don't have to memorize that. It's actually a handy thing to know, but you don't have to memorize that. I'm pretty sure it's 58, I think it's like 5,830 Kelvin. What does that mean? What is that a measure of?
The average kinetic energy.
Average vibrational kinetic energy of the molecules that make up the sun, right? So this is a measure of the average vibrational kinetic energy. Do some molecules have a bigger than average kinetic energy? Do some molecules have a less than average kinetic energy? Absolutely. Absolutely. Now, what are the molecules that make up the sun? Hydrogen and helium, what?
Gas.
Oh, hydrogen and helium nuclei.
Oh, it's plasma.
Right, because the sun's a plasma. But what, and that's actually moderately important. So we have this positively charged hydrogen, and we have positively charged helium that are vibrating back and forth like crazy, 5,800 Kelvin on average. That is ridiculous amounts of vibrating back and forth. And I suppose the solitary electrons, right, would be vibrating ridiculously back and forth as well. And what's the right name for the stuff that this emits? What's the right name for it? Electromagnetic radiation. Now, next year, you focus way more heavily on electromagnetic stuff. We only did a hint of electromagnetic stuff in topic 6. We're talking about well, really talking about moving charges, creating magnetic fields, right? But as it turns out, the only thing that creates electromagnetic radiation is accelerating electric charges. Accelerating electric charges, that's what creates these perpendicular electric and magnetic fields that rotate. So we have this positively charged helium thing that's vibrating back and forth. Is it accelerating? Yeah, absolutely it is. Absolutely. It's changing direction, right? It's changing velocity. Absolutely is accelerating. And it's doing it so fast that it actually has a pretty darn high frequency. Same thing with this electron, doing it pretty fast, really high frequency. And this thing vibrating back and forth is what creates these electromagnetic waves, right? So the peak wavelength emitted by the sun would correspond with the median vibrational kinetic energy of the molecules. That came out weird. I think it came out okay, but it came out weird, right? So let's say this guy's vibrating average. We might have a hydrogen, let me just stick with helium actually. We have a helium that's maybe vibrating less than average, right? And then maybe we have a helium that's vibrating way more than average, right? Vibrating like crazy. So this one might emit electromagnetic, it emits light, right? It would vibrate the charge, it's accelerating. It makes light. That is how all light, all radio waves are made, by vibrating charge. But maybe this one does this wavelength. Maybe this one that doesn't vibrate, that doesn't have as much energy, does this wavelength down here. And maybe this one that actually has way more than average vibrational kinetic energy. Do I have this backwards? Oh, shoot, I think I have this backwards. I do have it backwards. This one, I think is actually doing it over here.
Because the Earth was infinite.
Well, yeah, that wasn't what made me catch the error, but I think you're right. This one that has way more than average vibrational kinetic energy might be doing this over here. I'm sorry I messed up. But that's not important. What is important is that there is a range of wavelengths because there is a range of kinetic energies. But we do have a peak wavelength which would correspond with the average the temperature, the average vibrational kinetic energy. Alright, so let me shut up for a minute and ask what questions we have about this distribution of wavelengths that our black body is emitting. Jacob.
Does this mean we could figure out the number of
Based on the total
ions
power,
based off of the
the
total
total power and how far we are from it when we receive that. Yeah, maybe. Maybe. Seems like we ought to be able to do that. Other issues so far, we're not done with this graph yet, Moms?
Is there a reason that one slopes so much more sharp than the
Yeah,
other?
I think so. Well, I'm sure there is. But the reason I think that happens is because, kinetic energy is proportional to the vibrational speed squared. So we do get so a smaller speed is going to be disproportionately less power than a lot. I think that is what influences the slopes. That's my suspicion. I can't say that I've ever read that that's the case. All right, so let's keep going. So I have I have a few of these curves on this figure. So this one actually does say power on the y-axis, and this does have wavelength on the x-axis. But what we have here are 4 different curves that correspond with 4 different temperatures of our object. All right? So this one's at 2000 Kelvin, this is at 1750 Kelvin, 1500 Kelvin, 1250 Kelvin. So we actually have like somewhat of a similar curve for each one, where it is a little bit steeper as we go longer wavelength up to our peak, and then a little bit shallower as we go on the other side. But what's pretty striking is that the total amount of power changes dramatically as we heat up, and the peak wavelength shifts to the left as we heat up, like we might suspect, because if we have a higher temperature, right, the average molecule is vibrating with more energy, right? So we should be getting that shorter wavelength, higher frequency peak. These things are hotter than the sun or colder than the sun?
Colder.
Yeah, they're colder. The hottest one there is 2000 Kelvin. We said the sun was 5800 Kelvin, so it's a lot colder. And we can tell that just by the peak wavelength, right? Because visible is all the way over here. Even this thing at 2000 Kelvin is emitting practically no visible light. Maybe it would glow red a tiny little bit. So maybe this would be like the temperature of like the thing that glows in your oven, right, or in like your toaster oven. Maybe that would be about 2000 Kelvin. Maybe it would be 15, I don't know. We get a little bit of red, but not really. Most of the energy is still in the infrared. All right, so the 2 important things about as we change temperature is we get more total power as we get a hotter object, and the peak wavelength shifts towards shorter wavelength, higher frequency. Other questions about how a hotter thing's radiative power makeup is different from a colder thing? So we have a thermometer, right, that utilizes this to tell the temperature of things. So this doesn't send anything out. It can. I can hit a button, which I think will make it, I can make this do a laser. Yeah, see that now has a laser, but that's just to help aim. The laser doesn't actually do anything. Just I don't want to aim you guys with the laser on. But all that this does is analyzes, it's got to be analyzing the wavelength that it's receiving. Because if it wasn't doing the wavelength, if it was doing the amount of infrared, then that would change with a function of distance. But if it's just looking at the wavelengths, the peak wavelength, that should be enough to tell this thing the temperature. So let me go closer to Nick this time. Maybe if I go close enough and get him in a good spot, it'll show close to 98. So where's Mrs. Warnock put hers?
Ear.
Right, in the ear. So we put it in there. Oh, the laser's on. How did the laser get on? Now she actually sticks it in her ears, right? This is like 92 degrees, so it's kind of getting like the external ear, it's not really getting inside. That probably is though warmer than like, an arm or something, right? 91 is about the same, right?
91. 2.
Oh, why are you going to say 95?
It went to 95 and then went down, and now it's at 93. Now it's at 94. 94.
94, fine. So still not my core temperature, but we're getting close. right? What about the wall? What's the wall gonna be?
Room temperature.
30.
30 Celsius?
Oh, not Celsius. I was doing.
30
Probably
Fahrenheit.
70.
It's gonna be
73.
Yeah.
So it'll
73.5. Right? So the wall is at a colder temperature than me, so it is emitting a different peak wavelength than me. What maybe would be the hottest thing in here?
so the projector.
The projector's probably pretty hot. My computer might be pretty hot.
How does that work? Because we need something that's emitting like visible light, just emit visible light.
No, I think by the projector we mean the hot parts of the projector, not the...
No, but I mean like if you pointed it at the
Hold on. Let's finish with this. I'm pointing it inside the vent, and it says 133. It's pretty hot. I'm curious. It is pretty hot. I'm curious. My computer is actually not so hot. I don't think. Yeah, 85. I don't see anything else around that would be significantly different.
Light bulb?
Well, those are fluorescent, so they shouldn't actually be that high of a temperature, especially the bottom part. And I don't want to climb something to get up there, but let me turn the.
I do.
Wow. Oh, I have it on Celsius. It was 25.5 or Celsius. 78. A little warmer than that. A little warmer, but I wonder if the ceiling's actually a little warmer too. 78. Whatever. Anything else before we go to Liam? The desk. Well, the desk is black,
Yeah.
so that might be at a slightly higher temperature than some of the other stuff. Maybe.
What about the asphalt outside?
74.5, and this desk right next to it, which is a lighter color, 74.
Are you able to get the asphalt outside, or would it just get the one?
It's probably going glass, I think. No, I don't think glass is transparent to infrared.
Can we try?
I don't think it is. Well, it actually says 92.
Wow.
Well, let's try that glass.
Well, that glass is in the sun.
Right. Well, we could try the glass that has the blinds closed. 81, 90, 91, 92, 90. All right. Anyway, Leah, what was your question? All right. So I don't know exactly how this thing works, but I do think that it is analyzing the peak wavelength and then knowing what the temperature of the thing is as a result. Okay, so this should all be reviewed, right? The sun's peak emission is visible because of its temperature, right, which is very high compared to the Earth. The Earth's peak emission is infrared, right, because of its peak temperature, which is quite a bit colder compared to the sun. And then, how about, I think we already know this, but what's your peak wavelength? Visible? No, I can't see you guys in the dark, right? Your peak wavelength is infrared. So if we want to see you in the dark, we need to look in the infrared. Otherwise, right now I can see the light that you're reflecting. I can't see the light that you're emitting. I'm not sensitive to the infrared light that you're emitting. I'm only sensitive to what you're reflecting. All right, so these graphs are important to analyze, right, in terms of the peak wavelength. But what I want to do next, and we'll get a start on it, I don't think we'll finish, is the power, right? So kind of like the total power, not just the peak power, but the total power. So we do have a new equation that helps us do that. It's called the Stefan-Boltzmann law, and I'd like you to find it in your data book. I'd like you to find it in your data book. I don't think it looks exactly the way I have it up here.
No, it's a little different.
It's a tiny bit different, right? It just has the area over on the right, I think.
Yeah.
Yeah, so let's see. So this is so we have the albedo equation we already saw. We have an equation with a capital C that we'll do next time, and then we have an equation we have two equations with power. The top one is called the Stefan-Boltzmann law, and yes, it doesn't have the area on the left. It moves the area over to the right. So the Stefan-Boltzmann, what are the symbols in here? So the P is power, right? The T is the absolute temperature, so the temperature in Kelvin. What's the A? Surface area, right? Like our buddy the elephant, with the ears that have the large surface area. A is the surface area. And then what's the sigma? It's a constant, right? It's a constant. Guess what it's called?
Stefan
I believe it's called the Stefan-Boltzmann constant. Now let's find that in the data book, because here's where we have a slight problem. It is in here. Yeah, it is in here.
Oh, yeah. Oh, that's a weird, that's a weird.
Well, there's not two Boltzmann.
Well, there's the Boltzmann and there's the Stefan.
There's a Boltzmann's constant, which we don't care about, and there's the Stefan-Boltzmann constant, which we do care about, right? So it's the Stefan-Boltzmann constant, and it's the sigma, which is fine, because the sigma is in the equation in the data. So this equation, I think, is pretty cool, because when have we ever seen something raised to the fourth power? Well, I haven't seen anything yet this year raised to the fourth power. We don't see anything else this year raised to the fourth power. I don't remember seeing any equations in the data booklet for the stuff that we're doing next year with something raised to the fourth power. So I think that's kind of cool. So the total radiative power is super, super, super dependent on temperature. It's only directly proportional to surface area, right? But proportional to the fourth power of temperature. I think that's kind of cool. So what else? Let's get to a decent ending point here. Now, this is true for black bodies. This is true for perfect emitters. But nobody's perfect, right? So we do have a way to scale down gray bodies, bodies that aren't perfect emitters. And it's still kind of called the Stefan-Boltzmann equation, but we have an extra term in here. It's a lower, it's not a Greek letter, I don't think. It's just a lowercase e. And it stands for emissivity. I probably didn't spell it right. I think I have it on the next slide. I have it down here. Oh, I did spell it right. No, I didn't. Yes, I did. Go me. So if we have an imperfect emitter, then we just need to include this other term called emissivity. We can always use this version of the equation, and if we have a perfect emitter, we just use an emissivity of 1. If our emissivity is 1, then this is the same thing as our other version. All right? Most things that we use are perfect emitters. The sun is darn close to perfect. Even we are pretty darn close to perfect. The Earth is pretty darn close to perfect. We need relatively weird things that aren't so abundant in nature to have things with relatively small emissivities. Let me pause here for questions. What has a emissivity pretty far away from 1? Dr. O? It's an example of something with really low emissivity. Well, all right, so fine. Let's revisit. I actually, I don't really want to proceed in our last few minutes. So now, why don't we come back and talk about the sun and the black hole? So the sun certainly doesn't look black. How come? It's hot. If we cooled the sun down, it would be totally black. Right? It's a near perfect emitter. So it's not black just because of its temperature, but that doesn't mean that it's not a black body. It doesn't mean it's not a perfect emitter. We're pretty cold, right? And in the dark, we are black. Right? I mean, we're pretty perfect emitters. A black hole, I have to stand by that it doesn't emit anything. Maybe if we get right up in it, maybe then.
Who wants to find out?
But then it doesn't go anywhere, so, I mean, it certainly does absorb everything. I don't know. So what is a very imperfect emitter? I'm having trouble coming up with an example. A mirror? I mean, I know a mirror is really good at reflecting stuff. I suppose that means it's not very good at emitting for its temperature. I don't know, that might not be true.
We can Google it.
Well, we could Google it, but I don't want to Google it. The reason I don't want to Google it is because I know how IB handles it. And I'm going to give them the benefit of the doubt and say that they're handling it correctly, but I have some doubts. According to IB, albedo and emissivity are like opposite, right? So if we add the emissivity and the albedo together, we should get 1. So we know that like the Earth's albedo is 0.3. So that should mean, according to IB, that the Earth's emissivity is 0.7.
So why does
like I said, I have my doubts. There's really only one type of problem that this relationship crops up in, and we'll see it. But I have my doubts that that's perfect. I think for a narrow range of wavelengths, that might be perfect. I don't know that that's really truly perfect. Right.
So then snow would be like a near imperfect.
So snow would be a very poor black body, probably more of a white body than a gray body. I have my doubts, but that's how IB definitely wants us to handle it. So what we didn't do yet, we're actually not that far from being done with what I was hoping to accomplish today. We haven't done any quantitative examples using the Stefan-Boltzmann law, so we need to do that. But it's not very difficult, right? So we'll do this example when we show up on Monday. I still want to talk a little bit more about our buddy the elephant, but more importantly, things that we actually have engineered to be really good at giving off lots of radiative power. We actually call those things radiators, right? So we want to relate those to the Stefan-Boltzmann law. And that was actually my last slide. So we actually came pretty close to accomplishing what we wanted to accomplish. Let's remember that I do have a single problem for you guys let's do next time. So I am asking you to try and use the Stefan-Boltzmann law to calculate what your radiative power is. So you're going to need to know the Stefan-Boltzmann constant. You're going to need to estimate your surface area. You're going to need to know your Kelvin temperature and emissivity. Even if you're going to use one, you need to be stating that as an assumption. All right? So we have about a minute and 20 seconds to pack up. Patrick, you're welcome to. I made a statement a few times today that we're pretty darn good.